My name's Eli Horn, and this is my demonstration for an AC generator. First, I want to start by talking a little bit about Faraday's law. So as you can see, to create the highest possible induced voltage, in magnitude at least, you want to maximize the rate of change of your flux linkage. And flux linkage is simply the number of turns of wire you have times the amount of magnetic flux that's going through it. So the key is to have a lot of turns of wire and have a high amount of magnetic flux going through those turns, and then have a small amount just very quickly. So in other words, to vary the flux linkage as fast as possible. All Lenz's law really says is that there's a negative sign on that equation, and that the induced current is directed to oppose the changing field that produced it. A more common form of Faraday's law may look more familiar, and this makes sense because the higher the rate of change of your magnetic field fluxing through the surface created by the loops of copper wire, the higher your induced voltage. And here we see the basic setup I have for my magnets, with north pointing up and south pointing down, rotating in this direction. You want to make sure that you aren't rotating with your coils in this orientation, because although there's still a lot of magnetic field traveling through it, that it's not varying because your magnetic field is pretty symmetrical with this axis of rotation. So to show you, when I spin like this, which would be the orientation I just showed, there's pretty much no induced voltage. Now, when we do this, you'll see we'll have a lot coming out, and then as we turn, there'll be less and less and less and less, and then there'll be some coming in, and then more and more, and then less and less and less. So when we have this orientation for the coil, and we're still spinning in this direction, there is a high rate of change of flux linkage, which is a larger induced voltage. So now I'm going to show, now it's not great. I'm just spinning this, and we see there's a little something. So when we get a larger magnet, we make this magnetic flux stronger. So as you can see, we're actually making some type of dial movement. And the faster I spin this magnet, the larger the dial will move, where the slower I move the magnet, it moves a little bit less. So what you can also do, which isn't the most mechanically efficient thing, is literally ram up and down these magnetic flux lines through. So as you can see, when I go slower, there's not a lot. But when I go faster, there's a bit more movement. And that's because in this case, it has to do with velocity also, because the amount of flux linkage that you have going through, the amount of flux linkage you have is changing at a faster rate because your velocity going up and down is faster. One brief thing I wanted to add is that when I bought the wire, it was pre-packaged like this, and I thought that I could wrap it tighter or more efficiently, so I did this. I was completely wrong, and I ended up wrapping it probably a third as many times around as it was when it was pre-packaged. And what was funny is I noticed that the maximum magnitude of induced voltage that I observed was about a third as high as when it was pre-packaged. So that would make sense because the N was 1/3. So it was varying, it had less to vary. So the moral of the story is, don't try to beat a machine.